So, hello everyone. How are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna be taking a look at a book actually. And here's the cover of that book, and the book is Advanced Calculus Explored by Hamza El Zamiri. I think I'm pronouncing his name correctly. I'm not sure. And if I have done something wrong here, please let me know in the comment section, please. Okay. And this book is amazingly amazing, right? Because this book is like, if I talk about this book, so basically, this book has a lot of things. You can say everything. This book deals with like integrals, right? Obviously, calculus, sums, relation between integrals and sums, and graphs as well, like the function we are going to integrate or sum, the graph of that function. So basically this is an all-rounder, you can say, right? And that's why I think we should consider this book once. And I was thinking that I should read this out once, and then I just got a thought that, oh, it's been a long day. I just appeared on my YouTube channel, so I think let's just explain this. Oh, wait a second, actually. I'm just going to learn this book, and simultaneously I will be trying to explain it to you as well. So for that case, you just have to bear with me, right? And I haven't studied this book yet, but still, I know a lot of things. Maybe I'm not sure. And for that case, I'll be just explaining everything, whatever I would be learning out of it. And another thing I would like to share with you, I would be honest that if I don't know this one thing, if I don't know what is this, then I won't be like diving into that. I would be saying simply that, guys, I'm not sure about that thing, right? So obviously, it's a book which will be dealing a lot of things simultaneously. So for that case, and I haven't studied this book yet, so for that case, we need to be, or we need to develop ourselves that we can say that I'm not quite sure about that, right? But yeah, I can assure you that, like if I don't know about this thing, let's say I have this thing. So if I don't know about this one, so I will assure you that you will be looking at these things again in my on my YouTube channel later on, right? So yeah, it's sure that I will be explaining to you again, but not today actually, right? So I think let's just dive into it. Right. So let me just talk about the contents, and then we'll talk about the author, and then we will be just moving towards our main content actually, guys. So yeah, here's the contents. Okay, let's just talk about this. So first we have to talk about the author, and believe me, guys, believe me that when you look at this author, that is Hamza El Zamiri, you will be surprised to know about him. He is literally an amazing mathematician, you can say, right? Okay, we'll talk about that. Oh, sorry, we'll talk about him. Okay, and we have first part, that is introductory chapters, which includes differential calculus, and which sub includes the limit, which is L'Hopital's rule. And you know what, guys? I have had a YouTube video which was around 5 6 months ago. I have uploaded it on my channel. It was kind of old video of mine, so you can search it by just looking at the option of oldest, or you can say, yeah, oldest video actually, right? So in that specific video, I have used the L'Hopital's rule to solve an integral, right? And then we have more advanced limits. Oh, actually I need to talk about the theoretical part, and we'll not try a lot of questions out of it, please be assured about that. Okay, and then we'll talk about the derivative, right? The product rule, the quotient rule, the chain rule. Though we know about these things because I have used multiple times these things in my YouTube channel. I'm sorry, in my YouTube videos. And I think for now, for today, we just have to take it about these things. And if I would be having some time to explain you the next chapter, that is the basic integration actually, which includes Riemann integral, Lebesgue integral, the use substitution, other problems, exercise problems. So we'll talk about that as well. But but yeah, we'll talk about that as well. So now it's time to just take a look at the author part. Let's just talk about the author. Not talk, but let's just see the author, who he was and who he is. So here we are with about the author, right? So here's the author. Hi, my name is Hamza El Zabiri. Okay, let me just tell you something about him. So basically, he is. Oh, first of all, take a look at this. And I'm a senior 12th grader. Can you imagine that he was a 12th grader when he wrote this book? And you will be surprised to know that a 12th grader can reach up to those points where even I haven't reached yet. And you might have also reached yet there. I can assuredly say that. And it was in 2000 back he was in 12th grade back in 2019, and he published that this book. Just take a look at this guy, Hamza El at Central Valley High School, Virginia. Actually, he is like he belongs to Iraq, I think, as much as I could found on web about him. And obviously, I have always had an affinity for mathematics. And yeah, you can read this out if you want, but literally, he was great. He is great actually, and he's doing. And you know what? Another thing that I could get out of web about him, he had graduated. He had graduated from the premier Stanford University. So now you can just take a look at this guy. So yeah, obviously these Ivy Leagues or the greatest institutions in US obviously gonna take the legendaries, right? Yeah, okay. So the book begins with this integral, and this integral evaluates to pi. Let's just talk about this. Okay, so basically, again, here comes the you can say the curve of the function that was. What was that? So that was square root of 1 plus x over 1 minus x. So basically, this curve is representing y equals square root of 1 plus x over 1 minus x. Right. Okay. So now we have, let's just consider it this integral as I. So we can split this integral. Obviously, we know that if integral from it's like from a to b of f of x dx. So that can be written as integral from a to c of f of x dx, and plus integral c to b f of x dx. And the condition applied here is that c must be belonging between a and b, obviously, right? So yeah, basically 0 is belonging, like 0 is in between minus 1 and 1. So we can write this integral into two separate integrals, that is integral from negative 1 to 0 of this function, and plus the integral from 0 to 1 of this function. You know what, let's just understand this with the graph. So basically this is your 0, right? So this part and this part would be giving us the integral of this whole part. So that's it. It's not difficult to understand. And now what he did is he just substituted x, like you can say he replaced x with negative x. So that's gonna be giving us the first integral is gonna be minus, basically this minus dx. The minus is just in front, minus is there in front of like this factor, right? And we have the integral from 0 to 1. I'm sorry, 1 to 0 actually, because when you talk about limits, basically let me just explain it to you. So for this integral right over here, this one. So when you replace x with minus x, so basically, and you have to replace dx with minus dx. So your minus would be in front, and if we talk about limits, So when x is minus 1 here, wait a second. So when x is minus 1, your this x would, yeah. So basically when x is minus 1, so this is gonna be 1. And when x is 0, so minus x is also 0. So basically, yeah. And that's gonna be giving us 1 to 0. And this is gonna be 1 minus x over 1 plus x dx, right? And you know what? This minus would be helping us to just change the bounds of the integral, because that's an improper integral. So for that case, it's the integral becomes 0 to 1 of the square root of 1 minus x over 1 plus x dx. And that's what there is. So basically this is the integral. And now we can just add these two functions up, integrating from 0 to 1. And now we can write this as like cross multiplication. Basically it's this times this and this times this and this times this. So basically we have 1 minus x, because square root of 1 minus x times square root of 1 minus x is just 1 minus x, and plus 1 plus x. So we can see that x and x getting cancelled out over there, and we will be having 2 in the numerator, so that can be factored out as a constant. And we have in the denominator we have 1 minus x, I'm sorry, square root of 1 minus x times 1 plus x, which can also be written as 1 over square root of 1 minus x squared. Okay, and now let me just explain this to you from scratch. So basically we have integral of 1 over the square root of 1 minus x squared dx, right? And now substitute here x equals sine theta. So when you replace, actually when you take the derivative of this equation, so that's going to be giving us cosine theta d theta, right? So basically integral becomes cosine theta d theta over the square root of 1 minus sine square theta, right? And we have cosine theta d theta over this, can 1 minus sine square theta can be written as cosine square theta, right? And square root of cosine square theta is just cosine theta, which is we would be getting rid of these two cosine thetas. And finally we would be having integral of d theta, which is theta. And what is theta? When you just talk about theta from this equation, so theta is coming out to be arc tan, I'm sorry, wait a second. Theta can be written as arc sine of x, or maybe you can say arc sine of x. So from here you can say that finally your integral, that is integral of 1 over 1 minus x squared, is coming out to be arc sine of x plus c, right? So yeah, so basically the antiderivative of this function is arc sine of x plus c. So that's what it's there. So yeah, the derivative of arc sine of x is 1 over the square root of 1 minus x squared. So basically that's it. So basically that's gonna be giving us 2 times integral from 0 to 1 of, yeah, 2 times arc sine of x from 0 to 1. And here when you replace x with 0, so arc sine of 0 is just 0. But when you replace x with 1, so that's going to be giving us arc sine of 1, which is pi over 2. And that's going to be simply giving us pi. So yeah, that was pretty easy, isn't it? Okay, so basically he just talked about the integral, how did we evaluate it, or yeah, that's kind of amazing. This book is really amazing because this book talks about everything. Yeah, yeah, everything. Okay, and there is another proof. We can multiply that integral with this function, the square root of 1 plus x over square root of 1 plus x. So what's that's gonna be giving us? Let's just check this out. So basically we have, what we had is we have this thing. So if we so integral from negative 1 to 1 of the square root of 1 plus x over 1 minus x times 1 the square root of 1 plus x over square root of 1 plus x dx. So in the numerator we would be having 1 plus x only, and in the denominator we would be having the square root of 1 minus x squared, right? Okay, and now what we can do here, we have we can just write this integral into separate integrals, that is integral from -1 to 1 of 1 over square root of, wait a second, the square root of 1 minus x squared dx, and then we have plus integral from -1 to 1 of x over the square root of 1 minus x squared dx. And guess what? We can divide and multiply this integral with 2. So basically, the derivative of 1 minus x squared, when you replace 1 minus x squared with t or maybe t squared, in order to get rid of the square root, so that's going to be giving us minus 2x dx equals 2t dt. Oh wait, you don't need to just care about these twos. Yeah, I hope you guys are getting all the things. So we would be getting rid of these twos, and we would be having x dx as minus t dt. And that's where you can solve, like that's how you can solve this integral. And this integral is just arc sine of x from -1 to 1. So that's it. It's kind of easy, right? So both of the ways you can just perform, like just take a look at this. He did the same way, and believe me guys, I have never saw this book again. Like, I haven't saw this book this way, just going page by page. So please believe me. Yeah, it's kind of amazing. Okay, so basically he just let u equals 1 minus x squared, right? And when you, yeah, you can take u squared as well. So yeah, it won't bother you at all. And when you solve that, so you're gonna get pi again. So yeah, that's kind of amazing. Okay, so and this is the graph of y equals um, x over the square root of 1 minus x squared. So yeah, and that's why this book is kind of amazing, because you can just take a look at the functions graphical way. So graphical understanding is kind of amazing, right? Okay, and yeah, we have an amazing property here. We know about these things actually. We have used this property oh, a lot of times actually, right? Okay, and this one is kind of yeah. Should I try to prove this out? Oh, wait a second. Let's just try this out. So we have. I think I should use black color instead. I need some space. Okay. So basically, we have integral from a to b of f of x dx. Wait a second. I don't want to just take. Well, I don't want to just write that x instead. I'm happy with that x. So we can replace x with a plus b minus x. Let's just try this out. Okay, and we have dx as minus dx, right? If we talk about the derivative with respect to x only, because a and b are constants. So, okay, and if we talk about, wait a second, I think I should use z instead of x, right? So, okay, and if we talk about limits, so when x is a, so a plus, wait a second, a equals a plus b minus z. So a cancels out and z is coming out to be b. So basically your lower limit of the integral is gonna be b, and your upper limit is gonna be a. You can check that out. And we have f of a plus b minus z, and we have minus dz. And again, with the property of like the minus integral from, you can say, yeah, so we can just change the bounds. So it's coming out to be integral from a to b of f of a plus b minus z dz. And yeah, z is just index variable, so we can replace it with x as well. And be cautious here that this is a definite integral, and then only you can do that. But if it was an indefinite integral, so you couldn't do that. So be careful about that. So basically here we have the integral from a to b of f of a plus b minus x dx. So yeah, it was kind of easy and I loved to prove that down. And maybe this book will discuss the proof as well. Oh, I'm not quite sure about that, but we'll just take a look at that. Wait a second, let me just fix my ACL. It's kind of hot in my area a lot, so I have to suffer with that. But it's all right, guys. I'll be doing. Okay, so now we have what we have done is okay. So remember, we had integral from -1 to 1 of the square root of 1 plus x over 1 minus x dx, right? So now, if we consider f of x as the square root of 1 plus x over 1 minus x, and yeah, so basically f of a plus b. So here you have a and b. Your a is, this is your a. I'm so sorry. This is your a and this is your b. Your upper bound is b and your lower bound is a. So when you add both of them up, so that's going to be giving us 0. So basically 0 minus x, right? So basically it's minus x. So f of minus x is going to be the square root of 1 minus x over 1 plus x. And again, integral from -1 to 1 of your f of x dx is equals integral from -1 to 1 of f of minus x dx. And that's how we wrote this f of minus. Basically this is your f of minus x and this is your f of x, right? So we just have added f of x plus f of minus x them up, and we know that f of x equals f of minus x, and that's how we can write this as 2 times of integral, and then we just added the functions with each other. And there we are again reached to our same spot where we did reached a while ago. So that's how you can just evaluate that integral up to I. I'm sorry, pi, not I. Okay, okay. We haven't done complex analysis yet, so I think I don't cert to name that constant. Okay, okay, and here we have a preface. Let's just read this out as well. What's the value of x squared integrating from 0 to 1? Oh, that is kind of a difficult question. You know what? Why it's difficult? If you don't know this integral, you know what, in India, if I talk about in India, so when we just enter in class 11th, so in standard 11th you can say, so we just teachers usually memorizes us, like forces us to memorize this formula. And guess what, on my YouTube channel you will get this, the proof of this crazy integral. And this integral is being using over here, right, is being used over there. So basically for n equals 2, we have integral from uh, x, integral of x squared dx is x to the 2 plus 1 over 2 plus 1, so it's x cubed over 3, and from 0 to 1, because our bound is from 0 to 1, so basically it's coming out to be 1 over 3, right? So don't just memorize formulas, guys, but you can look for the proofs of them as well, right? Okay, and now we have a pretty famous integral. This is amazingly famous, and this is kind of easy to do. Let's just try this out as well. So we have, guess what? We have just studied this formula, this reflection formula, in a to b of f of a plus b minus x, right? Dx. So for this integral, we have a equals 0 and b equals pi over 2. And guess what? Sine of pi over 2 minus x is cosine of x, right? We know that. So if we talk about this, so that's going to be giving us integral from 0 to pi over 2 as well. Natural logarithm of cosine of x. I'm sorry. Wait a second. I don't want to write that. So we have natural logarithm of sine of pi over 2 plus 0 minus x dx. So basically it's integral from 0 to pi over 2 of natural logarithm of cosine of x dx, right? I think I should use this small, like this thinner pen instead of the thicker one. Okay, okay. So we have that thing so far. So basically, integral from 0 to pi over 2 of natural logarithm of sine of x um, dx equals integral from 0 to pi over 2 of natural logarithm of cosine of x dx, right? Okay, yeah, that's amazing. And now what we can do here is, what we can do. Wait a second, let me just think this out. Natural logarithm of cosine of x, and should we just add them up? But what's that's gonna be giving us? Wait a second, guys. I think I gotta think about this for a little minute, for a little moment. Okay, and now what we have to do is, let's consider these two integrals as I. So what we need to do here is we just have to add these two integrals up. So that's going to be giving us integral from 0 to pi over 2 of natural logarithm of sine of x plus natural logarithm of cosine of x dx, right? And using the natural logarithm property, so that's going to be giving us integral from 0 to pi over 2 of natural logarithm of sine of x times cosine of x dx, right? Okay, and yeah, and now what we have to do here is, wait a second, I need some blank page. Yeah, here we are having. Okay, so far we have went through the integral from 0 to pi, or pi over 2 actually, of natural logarithm of sine of x dx, and we have proven this integral equals to natural logarithm integral from 0 to pi over 2 of natural logarithm of cosine of x dx as well. So we have I, and if we just add these two integrals up, so that's going to be giving us integral from 0 to pi over 2 of natural logarithm of sine of x times cosine of x dx. And now what we have to do is we have to multiply, um yeah, oh wait a second, yeah, we just have to, yeah, so integral from 0 to pi over 2 of natural logarithm of 2, right? And plus integral from 0 to pi over 2 of natural logarithm of sine of x cosine of x dx, and minus integral from 0 to pi over 2 of natural logarithm of 2 as well, right? To just neutralize those things up. And here we can combine these two integrals, and that's going to be giving us, wait a second, integral from 0 to pi over 2 of natural logarithm of 2 sine x cosine of x dx, and here we have minus natural logarithm of 2 integral from 0 to pi over 2 of dx, and this can be written as integral from 0 to pi over 2 of natural logarithm of sine of 2x, right? Because sine of 2x is just 2 sine x cosine of x, and we can write this as minus 2 natural logarithm of 2 pi over 2 minus 0. And now what we can do here, let 2x equals t. So pi over 2 is gonna be, when x is pi over 2, so t is gonna be pi, and when x is 0, t is 0. So dx is gonna be 1 over 2 dt. So basically integral from 0 to pi of natural logarithm of sine of t, and we have dt over 2 1 over 2 integral from 0 to pi of natural logarithm of sine of t dt, right? Okay, and now what we can do here is, you know what, guys, there is a crazy property, right? There is a crazy property that says, um let me just explain it to you. So basically we are having integral from 0 to pi, right? And this can be written as, wait a second, let me just use the red pen. Integral from 0 to pi, this can be written as integral from 0 to pi over 2 plus from pi, I'm sorry, pi over 2 to pi. And guess what, these two areas are same, so that's how we can uh, just write those things as integral, I'm sorry, 2 times integral from 0 to pi over 2. So that's what we are gonna do here. So basically it's 1 over 2 times 2 integral from 0 to pi over 2 natural logarithm of sine of t dt. So that's gonna be giving us integral from 0 to pi over 2 natural logarithm of sine of t dt. Guess what, like this integral surprisingly, this integral surprisingly evaluates to I only, because this is I, or I actually. Just take a look at this. So finally we can say here, that 2I equals I minus your pi over 2 natural logarithm of 2, and finally we can subtract both sides with I, so that's going to be giving us I equals minus pi over 2 natural logarithm of 2, hence proved. Actually this is the value, so this is kind of amazing, isn't it? Right. So now let's just move a little bit further. Okay, now we are here with our introductory chapter, so let's just dive into it. Okay, differential calculus. So the limit. Oh, okay. First of all, guys, I'm so sorry that I haven't done epsilon delta function. But let's just read this out once. So we have let f of x be a function defined on the interval a of a comma b actually, except possibly at x naught, right? Where x naught is in the interval, that is, so basically x naught lies between a and b, right? Then the limit is limit x tends to x naught of f of x equals L, right? If for every number, this is your epsilon greater than 0, and there exists a delta greater than 0 as well, such that your absolute value of f of x minus L is less than epsilon. Whenever x minus x naught, the absolute value of x minus x of x naught is greater than 0 and less than delta for all x. So yeah, as far as I can read the definition, it's kind of obvious, but still I need to read about this a lot in detail. So for that case, I need time. But I can assure you that I'll be here in front of you with all the detailed information about epsilon delta function, because it's amazing and it's important, because in you can say in mathematical analysis, it's kind of, this is the base, you can say. So for that case we need to talk about this, but I haven't done yet this thing, so I won't be discussing this anymore. But yeah, if you want, you can just like just take a look at this. Prove that limit x tends to 0 of sine of x over x is 1 using the epsilon delta definition of a limit. So yeah, this just take a look at these things. So yeah, it's kind of amazing, but I'm so sorry that I haven't done this yet. So again, I'll be just skipping this. And now let's just talk about L'Hopital's rule. So L'Hopital's rule is one of the most widely known limit properties It states that if two functions f and g are differentiable on an open interval I with an exception made for a, and the limit of their quotient takes an intermediate form such as 0 over 0 or infinity over infinity, the limit of their quotient can be expressed as, just take a look at this. Limit x tends to a of f of x over g of x is also equals limit x tends to a of f dash x, or you can say f prime of x over g prime of x. Given that g prime of x is not equals to 0 and the RHS exists, obviously this is mandatory. Okay, so find the value of limit x tends to infinity of this function. So that function can be written in several ways, which is, but the first one is this thing, e to the minus x over 1 over x, and it's x over e to the x, right? So now we have, this is your f of x and this is your g of x. So basically if we use the L'Hopital's rule, so the derivative of x is just 1 and the derivative of e to the x is just e to the x. So basically we would be having L equals limit x tends to infinity of 1 over e to the x, which is 0, because like x is uh, it is an exponent, right? So the value of this would be tending to infinity, and when 1 over infinity, so basically it tends to 0. So that's how it comes out to be 0. And the the amazing part of this is that he just checked this out numerically, confirm our result. We can use Wolfram desktop or Mathematica. So basically what he did is just type the code and he just got the output as 0. So that's it. That's really you can say that's the perfect use of those things when you just when you're not sure about your results, so you can just check that out after just doing some code. Okay, and now we have another limit. And yeah, oh wait a second. After looking at that, we can say, as far as you can uh, notice there, we know that the definition of e to the x is limit n tends to infinity of 1 plus x over n to the n, right? So basically it looks like something sort of that when x is 1. So basically this is when n is infinity, it's just e, and it's kind of e over e, so it's 1 over 1 to the n. So we just have to take the derivative of this part. So yeah, so basically when you replace x with 1 here, so it's e coming out to be limit n tends to infinity of 1 plus 1 over n to the n. So that's is there written in the numerator. Okay, so define L equals limit n tends to infinity of 1 plus 1 over n to the n over e whole to the n, right? And now he just took the natural logarithm of this equation. So that's going to be giving us natural logarithm of L as limit n tends to infinity of n times. So basically this n, take a look at this. This n is here, and we had this part. And now what we can do, we can take further natural logarithm of this part. So that's going to be giving us, this part would be here, so it's n squared natural logarithm of 1 plus 1 over n and minus natural n. So basically you have this n, so this n is there, and natural logarithm of e is just 1, right? Okay, and now we can just factor 1n out of it, right, out of these two parts, and we can write that n with 1 over n in the denominator, and we would be having natural logarithm of L equals limit n tends to infinity of n times natural logarithm of 1 plus 1 over n minus 1 over 1 over n. And now what he did, he just took the derivative of the numerator and the denominator. So basically, natural logarithm of L equals limit n tends to infinity. And when you talk about the derivative of the numerator, so it's taking the derivative of the first part with respect to n. So the derivative of n is just 1. So this the first part is this. And next we would be having the derivative of this part. So so basically it's 1 over this part, so it's in the denominator, and we are having the derivative of the inside with the you can say with the um, chain rule. Yeah, chain rule. So for that case we would be having n times 1 over n squared, because yeah, this part, this n is there, and the derivative of this, the argument of natural logarithm is minus 1 over n squared. So there is the minus 1 over n squared, and the derivative of 1 over n is just minus 1 over n squared. So minus minus cancels out, and n cancels out, and finally we can say it's coming out to be limit n tends to infinity of natural logarithm of 1 plus 1 over n minus 1 over 1 plus n. So basically this is this minus minus cancels out, and this n cancels out. We are having n over 1 plus 1 over n, and that can be written as n plus 1 over n, right? So yeah, wait a second. Wait. It's 1 over n, not n, right? So basically we have n over n plus 1. So finally it's 1 over n plus 1. So yeah, that's how it just came out to be, something sort of that. And he just cancels out with the negative sign. Okay, so natural logarithm of L, limit n tends to infinity. And again, he just took the derivative, I think. Yeah, he surely took the derivative. And this time we had this part. So we have 1 over 1 plus n, right? Wait a second, let me just check this out once. The derivative of this is, yeah, it's n plus 1 to the minus 1, right? So it's minus of n plus 1 to the minus 2, which is minus 1 over n plus 1 whole squared, right? So yeah, this part is there. And the next part is we have natural logarithm. So basically we have natural logarithm. So the derivative of natural logarithm is coming out to be minus 1 over n plus 1. Wait a second, let me just check this out. So it's 1 over 1 plus 1 over n, and it's minus 1 over n squared, right? Okay, and we have, wait a second, again I'm simplifying, we obtain. Am I doing something wrong there? Okay. Wait. I'm so sorry. I'm so sorry. What he did is, I think I need to check this out, because when you talk about this part, so basically when n is tending to infinity, so 1 over n is just 0. So basically natural logarithm of 1 is also 0, right? So we are left with limit n tends to infinity of minus 1 over n plus 1 over minus 1 over n squared, right? And now we have to take the derivative of this part. But where does this n coming out to be? Coming out from? Wait a second. Had I done something wrong? I'm not quite sure. Wait a second, guys. Let me just figure this out, and then we'll just talk about this. Yeah, guys. Um, I just got the thing where this is coming out. Actually, it's this book should have discussed this in several steps, but it's all right. It's kind of jumped off a quite big step. So for that case, let me just explain it to you. Okay, so first of all, we had what so we had this we had reached up to that point, right? So let's just talk about that. So we have uh do I have some blank page? No, I don't. I need to suffer there. Okay, that's all right, we can. So we have limit n tends to infinity of natural logarithm of 1 plus 1 over n minus 1 over 1 plus n plus 1 over 1 minus 1 over n squared. Okay, okay, so that's perfect. Yeah, that's perfect. Wait a second. Yeah, yeah, that's kind of good. That sounds good. And now what we have here is okay. So yeah, and now we have to use the L'Hopital rule again here. So for that case, we have to take the derivative of this part and this part as well, and we have to take the derivative of this part as well. So the derivative of d over dn of natural logarithm of 1 plus 1 over n is it's 1 over 1 plus 1 over n, which is n over n plus 1, right? Okay, and if we talk about the derivative of minus 1 over n plus 1, so that's going to be giving us 1 plus 1 over n plus 1 whole squared. And if we just add these two things up, so it's n over n plus 1, right? Wait a second. Hey, wait. Am I doing something wrong there? Oh, wait. Let me just check this out again. Again, I did a mistake. Actually, I should have used the chain rule as well. So with the chain rule, we are having it's minus 1 over n squared. So basically, it could be simplified as 1 minus 1 over n times n plus 1, and adding 1 over n plus 1 whole squared, and we can just multiply n plus 1 and divide with n plus 1 in order to get n plus 1 whole squared in denominator, and here we can multiply n and divide with n plus 1 whole squared in order to get these two denominators same, right? So now we have minus n plus 1 plus n over n times n plus 1 whole squared, and from here we can say minus n minus 1 plus n over n times n plus 1 whole squared, and finally we just got rid of these two n's, and finally we are having minus 1 over n times n plus 1 whole squared. So yeah, that's how we just got raised up to there, and uh, it should have written some two steps, at least two steps it should have written, but it's all right. And the derivative of the denominator, it's just 2 over n cubed. So yeah, that could be simplified easily. And we have minus of limit n tends to infinity, and basically this part would be in the numerator, so it's n cubed, and we have 2n times n plus 1 whole squared, right? Okay, and we can see that expanding the denominator, okay, would result in a first term of 2n cubed. Yeah, yeah, right, right, 2n cubed. The okay, and from here we gotta think about this a little bit. Expanding the denominator, right? Expanding. So it's expanding basically means n cubed over 2n, and it's n squared plus 1 plus 2n. So it's n cubed over 2n cubed plus 2n plus 4n squared, right? And next what, dude? Next what? Like how could you write this as minus 1 over 2? minus 1 over 2. So when n is tending to infinity, so n cubed over n times n plus 1 whole squared, n cubed. Wait a second. I need to think about this a little bit. Okay, guys, I just figured this out. Basically, what we have done here, we can ignore rest of the terms, and we are having n cubed over 2n cubed, right? And rest of the terms like 4n, uh, actually 4n squared, and it was, what was that? It was 2n, right? So we can just ignore these things up because they are way too small, because n is tending to infinity, right? So we can just ignore them up. And finally, we just got rid of these n cubes as well. And finally, we would be having 1 over 2, which results out in natural logarithm of L equals minus 1 over 2. And here, uh, by using the ratio of coefficients, yeah, actually, basically it's, wait a second, let me just use the black color. So L is coming out to be e to the minus 1 over 2, which is 1 over square root of e. So yeah, that just resulted out in something sort of that. So that's kind of, yeah, again, using the Mathematica he just used. This is kind of amazing, guys. I'm just gonna use this down. I haven't used that yet, but yeah, I'll be using that. Okay, and we have more advanced limits. Define the Riemann zeta function. Wait, guys. This is the thing we love to talk about, because I have literally talked about this multiple and a lot of times. You can just find, you know what? I have made a playlist as well on Riemann hypothesis, and which I have just you can say I have placed all the Riemann zeta functions or function videos in that playlist. So I would request you to just consider that playlist once. Okay, so yeah, we know that this is the Riemann zeta function. Find limit s tends to infinity of Riemann zeta of s minus 1 whole to the 1 over s. So Riemann zeta of s is just the sum as n is going from 1 to infinity of 1 over n to the s, which is 1 over 1 to the s, 1 over 2 to the s, 1 over 3 to the s, and that just keeps going up to infinity. Okay, okay, so this is the graph of this function, which results out to be something sort of this. Okay, now let's just assume that L equals the limit that we are here to evaluate. Yeah. Oh, I'm sorry. I just let me just, yeah. Now it's good. And next we just have to replace this zeta function with its definition, right? Right? Okay. We just got rid of these ones, and we are here limit s tends to infinity of 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s whole to the 1 over s. We proceed to factor 1 over 2 to the s. Okay, so we just have to factor 1 over 2 to the s out of this that right hand side. So basically we would be having limit s tends to infinity of 1 over 2 to the s, and we are having 2 to the s over 2 to the s plus 2 to the s over 3 to the s plus 2 to the s over 4 to the s plus dot 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 up to infinity, and it's your 1 over s. So basically when you just try to just remove this, actually when you just try to factor this out, so you just have to consider that s cancels out with this s, and you would be just getting 1 over 2 out of it, right? And you can just combine these things up, so that's going to be giving us 1 plus 2 over 3 to the s plus 2 over 4 to the s, or you can say whole to the s. So basically, when s tends to infinity, all terms inside the parenthesis with s as an exponent will approach 0. Yeah, obviously, because when s is tending to infinity, this is just increasing, but this exponent is like reducing. So basically, that's gonna be giving us wait a second. Yeah, it's 1 over 2 this part, and we have, yeah, so this part is gonna be 0. Yeah, I think, let me just think this out once. Yeah, yeah. Wait, actually. Because when s is tending, wait a second, basically this is 2 to the s and it's 3 to the s. So basically, when s is tending to infinity, this part is just like this part is infinity, right? And basically 3 to the infinity is always greater than 2 to the infinity. So for that case, we can consider this it's tending to its 0, and hence we can say all these parts would be tending to 0, and we would be just having 1 to the 1 over s of along with a factor of 1 over 2. So s tends to infinity of 1 over 2 times 1 to the 1 over s, and basically 1 over s, when s is tending to infinity, it's just 0, and 1 to the 0 is just 1. So basically we are having 1 over 2 as our limit. That's amazing, guys. That's literally amazing. Okay, we have defined a double factorial. Well, we know about these things. We don't need to talk about them separately. Okay, so yeah, these are some, you can just try this out, this limit. And now I think I should just proceed further. Yeah, okay. We have a theorem. Let's just read this out. Stirling's approximation or Stirling's formula is one of the most common approximations for factorials. The general formula is natural logarithm of k factorial equals k times natural logarithm of k minus k plus o of natural logarithm of k, where big O notation indicates that the left hand side describes the right hand side's limiting behavior, that is, as k tends to infinity. So basically, Stirling's approximation is valid when the value is tending to infinity, and this is an amazing formula. Literally, it's an amazing. And here n should be very big, so n is tending to infinity basically. So this is an amazing stuff. Okay, I think he did use this Stirling approximation into this yeah, the evaluation of that double factorial limit. Yeah, that's kind of amazing. Okay, and here we have the Fibonacci sequence. Let's just try this out once. So basically, you know what? The beauty of Fibonacci sequence is your first term and the second your look. Let's say that A1 is your first term, right? A sub 1. So your A sub 2 is A sub 1 plus A sub 0, which is basically A sub 0 is 0, and A sub 1 is your 1. So basically, when A sub 1 is 1, so your first term is 1, and your second term, which is A sub 1 plus A sub 0, which is 1 plus 0, which is 1 as well, and your A3 is A sub 2 plus A sub 1. So A sub 2 is your 1 and plus A sub 1, 1. So your third term is 2, and A4 is A3 plus A2. You can see the sum of the last two consecutive terms is your term, right? So your A3 was 2 plus 1, which is 3. So your fourth term is 3. And your fifth term would be 5. Sixth term would be 8. Seventh term would be 13, 21, and dot dot dot. That's just keeps going up to infinity. So that's your Fibonacci sequence. And actually, there is a perfect definition. Instead of just getting confused with my definition, you can just read this out. This is kind of perfect, you can say. Define the nth Fibonacci number as f sub n equals f sub n minus 1 plus f sub n minus 2, where f1 equals f2, which is 1. So, yeah, you can understand the Fibonacci number, or you can say the Fibonacci sequence. And here we have a limit n tends to infinity of f sub n plus 1 over f sub n. Okay, so basically, when in this very equation, when you replace n with n plus 1, so your f sub n plus 1 is gonna be